Hi everyone, this is Mr. Lee. In this video here, we're going to go over the skill of linearization. Now, linearization is something that we will do for the entirety of the year, and it is a very common type of problem that they ask for FRQs. So, let's begin. At this moment, what I would like for all of you to do is just pause the video and quickly just sketch and write out what I'm about to box in through this highlighted portion. Okay. All right. So right there. Wonderful. Now that you've done that, let's go over what exactly this means. So these are the four common trends in physics. So just a quick little background. Physics is the language of the universe. So everything that we learn about here, and even in the formulas, is just describing what naturally occurs in our reality. And it just so happens that all those things, mathematically speaking, follow very common trends. Now, these aren't the only ones, but these are the most common types. So we'll go over it right now. And I just want you to know that the top row are all the quote-unquote the positive ones, and below are all of the negative ones. So those are just a couple of examples. Okay. So let's try this. So the first one is a linear proportionality. So it's just the straight line version, meaning that it's like it's a ratio that you can follow. Like for example, for every 1 there's 2. So for every 2 there's 4. For every 3 there's 6. Right. So so on and so on and so on. It's directly proportional. You can follow the trend set. Okay, and the important thing is that you can follow along. So if one goes up, the other one goes up. If one goes down, the other one goes down. Okay, directly proportional. And this right here was actually our car lab. So we know that for the car, for every 1 second that passes, it will travel a certain distance. Okay, it's predictable. The next one is what we call the square proportionality. Okay, so it increases at an exponential rate, or a square proportion rate. Now, here's the other thing that is important. The max is never reached unless there's like a physical reason as to why we would even reach the max. So it just keeps on going up and up and up and up. Okay. Now, in terms of the slope, because one of the common types of questions that we'll see is, what does the slope represent? And so us being able to identify what's happening to the slope is important. So I'm just going to do a quick reminder that here, in order to figure that out, right, you just draw the tangent line at the beginning. So that looks pretty flat. And then you draw the tangent line towards the end. And so that right there is, pretty much vertical. So we can say here the slope is increasing. And we can see the same here. In the beginning, it's pretty flat, and then it gets pretty vertical downwards towards the end. So the slope is, in fact, increasing. The next one is a square root proportionality. And so the idea behind this is that a maximum value of whatever that y-axis variable is reached. So, for example, if the y-axis represents position, right, the max position is reached. Same idea with the slope, okay? The slope in the beginning is pretty big, and then it just like flattens out. Okay, so the slope is actually decreasing, so the rate goes down. So it doesn't continually increase, but the rate of increase decreases until it eventually reaches no rate of change, or a flat zero. And next one, we have a inverse proportionality. And the inverse proportionality, you are reaching a minimum value. So for example, here, whatever this y variable represents, such as position, right, is reaching a minimum value for that position. But the slope goes from a pretty steep magnitude, downwards of course, but steep nonetheless, a big magnitude to a magnitude of 0. It flattens out. Okay. Now, in the top row are the mathematical functions. So if you were to plug this into a calculator, okay, these are the shapes that you would get. Okay, so with that being said, let's go over the actual process of linearization and the why, like why we need to linearize. So the purpose of linearization is that it makes the data easy to read, and it makes the data easy to communicate. So for example, what I mean by that is one of the things that we always have to do for physics and for our labs is you have to determine the slope. Okay. Now, for something that's curved like we see here, we can't like the slope is constantly changing. So because the slope is constantly changing, right? So here the slope is flat, and then the slope is getting steeper, 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 and then like very steep towards the end. We can't say what the slope is. And so through the process of linearization, we can now tell that the slope is a constant, right? And that meaning, remember, the slope always has a meaning. Okay, what does that slope represent? Okay, what does that numerical value of the slope represent? We can now say, because we can actually find the slope. Where here we can't find the slope because the slope is changing, but here, because the slope is constant, we can actually say the slope represents this. All right? So that's the whole reason why we linearize. It's so that we can communicate with others. Common mistakes that students always make is that you don't adjust the x and the y axis units and the variables, and I show you what I mean in our example problem. And of course, you should always be keeping track of the units because the slope, as I mentioned before, the slope tells you something very specific, and knowing the units of that slope can tell you, hey, for this kind of graph, the slope represents this, which helps us out. All right, so let's do an example. This is just a data table I came up with. And so the process of linearization, just so you all know, by the way, if you were to sketch this graph out, I believe it looks something like this. So we have a position versus time graph here. Okay, let me update this. There we go. So we have a position versus time graph, and it looks like this, and we've seen this graph before. This is what we did for the ramp lab. So it is accelerated motion. So when we linearize it, okay, what we do is we go back to this handy chart that I told you all to copy down, okay, and we take a look at which shape our graph matches, and we can see that the graph matches this square proportionality. And so what you have to do is you have to adjust the y-axis variable and the x-axis variable so it actually matches the formula. So let's do that together. We know that the y-axis variable is x. Okay, so by the way, is y equals x squared. So the y-axis variable is position. And you see here, because it's just y, we don't have to adjust this, right? There's no changing happening, okay? We are not adjusting the math behind it, versus not time, because if you take a look here, right, time here is just time, but according to our formula, time should actually be squared. So it will be t squared. And the units that I mentioned before, you should always adjust the units as well. So mathematically speaking, our position column won't change because we're not changing anything through our linearization process because this formula says we don't have to. Okay, and just so you know, the most common types of problems for linearization, you're only changing one of the actual data sets. So for here, for the time squared, what we're doing is we are adjusting all of the time values by squaring them. So 0 squared gives us 0, 1 squared gives us 1, 2 squared gives us 4, 3 squared gives us 9, and 4 squared gives us 16. So what we see here is after we graph this, okay, if we were to graph the linearized graph, okay, and so I'm going to make sure I point out the common mistakes. So here, position and meters, that doesn't change, but instead of writing t for time that we did over here, okay, I'm going to make sure that my time is squared, and I'm going to make sure my units are also squared. So if I were to plot this out, I would actually get a straight line. And that is the process of linearization. You take a curved line and you turn it into a straight line of best fit. And now let's talk about the whole idea of the slope. So if you remember, one of the things that we talk about in class is that if you do change in y-axis over change in the x-axis, and you look at the units will tell you what the slope represents. Okay, and so for here, we have m for meters, which is the y-axis, and we have seconds squared, which is the change in the x-axis. So here the slope is the acceleration. Now I'm going to put the acceleration in quotes because it's not like just the acceleration. There's actually a mathematical reason as to why it's not just the acceleration, and that will come up in a little bit. Okay, but because the units are meters per second squared, we know that it is a acceleration of the object, right? So the slope represents something just like the acceleration. Okay. Now, there is a secondary method, okay, and the secondary method goes back to our previous example when I said the slope isn't just the acceleration, it's like a little extra, all right, and this method goes into the little extra part. So method 2, in the meaning of the slope, what you want to do is if you actually have the physics formula, so this is coming on later on in the year where we have all the formulas, with the formula sheets. One way to linearize your data is by comparing it with the actual formula itself. So if we had a position time graph, okay, and here these are what we call our kinematic equations. These are equations that represent accelerated motion, and we'll go into more detail on that in a future video. What you do for method 2 is you choose a formula that represents both your y and your x axes. So if we take a look at these three motion formulas, we see that the second formula has position and it has time within the formula. So the method or this method allows you to just make sure that your y-axis and your x-axis looks just like the formula, because these physics formulas are describing what's happening in our world, right? So this is based on our reality. And so if we base our graphs on our reality, we should get a linear line of best fit. And so we see here that the y-axis, right, if you're looking at y equals mx plus b, the y-axis is almost always on the left-hand side. So here, this is the y-axis, okay? And then if we take a look at the x-axis, which is just t, always take a look at the greatest exponent. We see that t should in fact be t squared. So that's how we know we needed to make our x-axis a squared for time squared to make it match this formula, okay? So if you do that and you adjust the data table by squaring your time, you would in fact get a straight line. Cool. Now, let's take a look at the meaning of the slope. So like I've been saying, it's like a representation of acceleration, and here is the details why. So if we take a look at y equals mx plus b, we know that position is the y-axis, and let me use my highlighter method here. Okay, we know that the x-axis is t squared. Okay, here, right, this is your x-axis, which is t squared. And so now the question is, what comes in front of this x-axis? And that is the slope. So if the question is, what does the slope represent? Okay, using this method, all you have to do is go back to the formula. The formula will tell you exactly what the slope represents. So if we take a look here, in front of the x squared, so let's make sure we highlight it, right? So this is our x squared. In front of all of that, we see the 1/2 and the a. So the slope represents 1/2 of the actual acceleration. Okay, and so yes, it is a value of the acceleration, but mathematically the slope would represent 1/2 of the acceleration after the linearization process, and that is because we linearized it, and when we linearize it and we line up, what is this? The y-intercept form, we know that whatever comes in front of the x-axis variable has to be the slope. And according to our real-life physics formulas, that would be 1/2 of the acceleration. Okay, and the units show that the units are meters per second squared, and that is acceleration. Anyways, that's it. I'll see you next time. Bye bye.